Hello friends, welcome to my new video and my channel too. Here I am gonna showing land surface temperature mapping. For this we have to download the Landsat data from Google Earth Explorer and we have to add a band 10 from that data on our GIS. And here I am going to add my thermal band 10 here. And it asks us for a transformational change, and here we can click S, go on clicking S. It asks us for a transformational change, and we can see here our thermal band 10. After this we have to calculate the TOA radiance, that L lambda, and we have to know the constant value ML constant and AL constant that we are using it in the raster calculator, and QCal means our thermal band. And for that we have to see a metadata that we have downloaded along with Landsat, and I have opened it, and we can see that this radiance multi-band ML band 10, this 0.34 3.3420 E minus 0.04, that means our constant value of ML, and here our constant value of AL, that means radiance addition band 10, and we are using this two value for the to calculate TOA spectral radiance. Now we are opening Arc toolbox, and we are going to spatial analysis tool, and then to map algebra, and then running the raster calculator tool and using the formula. And here we are gonna use that two constant value that we have get from the metadata, and we are gonna adding that formula, that is ML into ML means 0.333, not 3342 into that quantize or the thermal band 10, double click on that, plus put the addition sign, and that our addition band value or the constant value, that 0.1. Now save it on your desired location and click OK. Then we get our output of the TOA spectral radiance. Now we have to calculate the conversion to top of the brightness temperature. For that we have to use the formula that I am showing you in this code file. Oh sorry, it is conversion to TOA reflectance. Here it is, and top of the atmosphere brightness temperature, BT equal to K2 divided by logarithm bracket K1 constant and L lambda plus 1 minus 272.15 or 273, and we are gonna getting that K1 and K2 constant on our metadata file that we have downloaded from the Landsat along with Landsat. Now these are the two constant, K1 constant and the K2 constant for the band 10, to calculate the top of the brightness temperature, and we are gonna use it in our raster calculator tool. That here we are gonna use the formula K2 divided by for this we have to use that our immediate TOA spectral radiance data to. Here is the formula. I have done a copy paste. Now I am changing the mathematical logarithm function here. Sometimes GIS doesn't take the copy paste value, so I don't want to get any error, so that I am doing it myself without copying any data. Now here I am copying it and pasting in that our created logarithm mathematical function and deleting the before one that we have copied. Now we're gonna delete that bracket too. Now we have to put our TOA file at that place. For that we have to delete that and add our raster calculator file that we have got recently. And after that we have to assign our mathematical symbol properly, so that we can't get error or we can get the output easily. Close the bracket properly and save your output file in your desired location by giving your name. I am giving here TV, that means thermal brightness or the brightness temperature, top of the brightness temperature, and we have get it. Here we can see. Now after this we have to calculate normalized differential vegetation index, that means NDVI. For that we have to add band 4 and the band 5 from our Landsat data, and we are gonna dealing with land surface temperature, which we can get by through the land surface emissivity. So to calculate the land surface emissivity we need a proportion of vegetation. So proportion of vegetation index can be calculated by NDVI. Now for NDVI we have to add infrared band and the red band. I am gonna add band 4 and the band 5 to calculate NDVI. Now I am going to click yes. Don't worry. Click yes again. Now I am going to run mathematical tool in the raster calculator tool. Here I am going to use the mathematical function float and bracket open our band 5 minus band 4 by float band 5 plus band 4. After this we get our NDVI output, and first of all we have to recognize which one is band 5 and which one is band 4. So add it in our formula carefully, otherwise we can get lots of error while doing this, as we are using only raster calculator to calculate the land surface temperature. and here I'm gonna use this. Now, as I have said already, now I'm gonna assign my name and run it, and here we can get our value -1 low and the high value 1. Now I am going to its property and its source to see our maximum and the minimum value too, along with its mean and the standard deviation. Now I am going to symbology and assign a new color ramp. To look good or expressive output. I'm gonna use this and click on apply and OK. Now we can see our NDVI output. Now I am using this output to calculate proportion of vegetation PV again in the raster calculator. Before this I am going to show you this formula, that means NDVI proportion of vegetation formula. Here it is, NDVI minus NDVI minimum value that we have looked it up, and NDVI maximum value plus NDVI minimum value total square. And now I am using mathematical function square. It is there in the formula too, and I am gonna put my formula NDVI that I have told before, and I have done that formula and assign my name and run it. After that I am going to calculate the land surface emissivity here, as we have got PV value too. You can see the formula clearly here in the constant or the constant value. After this we are going to calculate land surface temperature. Now I am going to run raster calculator again and use the land surface emissivity formula on our map algebra expression. Zero 0.004 into our PV, double click on that, plus 0.986, and after this we can get our land surface emissivity value. Land surface emissivity I am gonna assigning it as our name. You can save it in your desired location or working folder. Click OK, and we are gonna get our land surface emissivity value. After this we are one step away from the land surface temperature mapping. For that we have to get familiar with its formula before calculating it. And I'm gonna use that formula here, TV by bracket 1 plus lambda, and here I am gonna show you lambda value, that means wavelength value of our band 10, as we are using thermal band 10. So here thermal band wavelength range from the 10.60 to 11.19. So I am gonna take an average of it. To calculate our land surface emissivity or land surface temperature mapping. Now that wavelength constant 10.8 is I have taken an average value, and plus TV, that our top of the brightness temperature raster output, divided by our another constant C2. Here we can get its value 14388 into logarithm mathematical function into land surface emissivity. Our output, and give it a name LST, that means land surface temperature, and I am giving it 10 as I have done it already, so we can get error of name, same name. And here it is the formula, but is little bit error. I am gonna edit it. Look at it carefully, what I am gonna do on this formula. It has got error. I'm gonna use bracket, no, not a curly bracket, big bracket, and I'm gonna use it here. Now this is our land surface temperature formula. You can see it, and I have used this formula in our raster calculator tool, and this C2 constant value and this BT constant is a BT value as we have got it from our second output. Now I'm gonna run it. You can observe it here, our high and low value, and this low value is that black line of our boundary data. It is not a error, and its high value is 52.69, and I am gonna change its color ramp. No, it looks similar, so I am gonna change my color ramp or invert my color ramp so we can analyze it easily. It looks sweet, as our map is temperature map, so it looks pretty good. Now this low value is of that boundary data. We can identify it by using the identify tool. I am zooming it. We can see the pixel value and see the temperature by putting the cursor on our data. And we can see here our pixel value 145, this low value. We can see we have got our output here, but due to this side boundary we are getting low value.